Okay, so this is the last video about pulse induction metal detectors. This is the audio stage. So remember from that video on the sampling integrator, the output of the sampling integrator is a DC voltage or near DC voltage that indicates the presence of a metal target under the coil. So when there's no metal, that DC output voltage is going to be minimal, let's say 0. And then when you get closer to a target, this DC output voltage gets higher, and it is maximum when you are right over the target. And then as you move away from the target, that DC output voltage is going to go down back to 0 or something close to it. So that's your DC output from the sampling integrator. And what we want here, what's the role of that audio stage? It's to transform that DC output voltage, or near DC, to a sound that gets louder as you go nearer to the target. So when you swing, if you don't have any metal under your coil, no sound. As you come closer to the metal target, the sound gets louder, and as you go away from the target, the sound gets lower until you're too far away from the target, and then there's no sound. So that's the idea. So it's based on loudness. So using loudness to indicate that there is a metal under your coil, that's one way to do it. The other way would be to use what's called a voltage controlled oscillator, a VCO. So when we talk about VCO, we mean that when you are away from the target, you have like a background sound that is usually pretty low in frequency. And then as you come closer to the metal target, the pitch increases. So in other words, the frequency increases. And as you get away from the target, that frequency decreases, and the pitch gets lower in terms of frequency, in terms of pitch. So that's called VCO, and that's another way to do it. But here we are using loudness. Okay, so why you do it one way or the other, I have no idea. But here I'm describing loudness. Okay, so let's look into this LTspice simulation. So it's basically kind of a common emitter amplifier. You can see the transistor here. So this is the base, collector, emitter. You have a resistor here, which is part usually of what we call the voltage divider bias. You have another resistor, but here it's not connected to the positive voltage source, the battery basically. V2 here is the battery. It's not connected. I mean, usually when you have a common emitter configuration with a voltage divider bias, this resistor would be connected here. So it's slightly different. Other than that, it's the same. You still have your emitter resistor here and your collector resistor. The output is right here on the collector. Okay, so it's very similar to a classic common emitter configuration, except here. And here, what we do is that we take the output, the DC output from the sampling integrator, and we use it to set the quiescent base voltage. So that's going to control the loudness, because let's say you have the DC output is 0 volt, so that you would get 0 here. So there would be no loudness at all because the transistor is turned off. Remember that you need 0.6, 0.7 volt right here, at least, to turn that thing on. Now, let's say that the DC output is 1 volt. In that case, the base voltage might be, I don't know, 0.7, 0.8. So it's going to turn on the transistor, and you would get the signal coming out here. So this signal would come out here. So that would produce a sound at a certain loudness level. Now, if you increase the DC output to, let's say, from 1 volt to 2 volts, this is going to increase maybe to, I don't know, 1.2 volt or 1.5 volt, I don't know. And in turn, this will make the transistor work harder, and this output will get louder. So that's basically how it works. So here what I did is that I used a parameter. So parameter X is the voltage here. So that's my DC output. And I'm going to step over two values of that parameter using a list. First value is going to be 1 volt. Second value is going to be 2 volts. And we're going to look at the various voltages here. So let's run this thing. And first, let's look at the bias. So this is the bias voltage. So it includes, it's the DC plus the AC. So when it's 1 volt, it's right here. And you get a quiescent base voltage of about 0.8. So in that case, the transistor is on, barely on, but it is on. So you're going to get one loudness level. And if you go to 2 volts, you get a quiescent base voltage of maybe 1.55, something like that, 1.6. So the transistor is going to be working harder, and you would get a louder signal on the output. So let's look at the output, which is right here. So here we're only going to see the AC. So it's going to be centered on 0. Basically, the green one reaches this level on either side. So this is the 1 volt level, and this is the 2 volt level. So what you get is an AC sine wave that's slightly larger in terms of amplitude, which means that you're going to get a louder signal. So that's about it. It's relatively simple. The values I put here, I mean, I kind of did it at random just to get something working. I'm not sure if it's the best way to do this. Probably not. I forgot to say, yeah, so you get that AC sine wave here, but then what do you do with it? Well, then you can probably use this output as input to another amplifier, and that will be able to drive a speaker or headphones, whatever. Okay, so of course in this video I kind of assume that you know about the common emitter amplifier set up using a voltage divider bias. I made a few videos on this, so we can have a look at them, but it's kind of an important circuit to know about. And in a few words I can kind of explain how it works. So usually, as I said before, this resistor is connected to the battery voltage here, and you don't have this part. And the role of the voltage divider bias is to basically set the quiescent base voltage in a way that's completely independent of the transistor. Okay, because you cannot rely on the transistor and that 0.7 volt differential here to set up your bias voltage at the base, because otherwise it's going to be too dependent on the transistor you use. So that's why you use this voltage divider bias. And this is by playing with those two resistor values, you can set the quiescent base voltage to whatever DC value you want. Typically it would be, I don't know, maybe slightly above 0.7 volt, maybe, depending on your AC signal. It depends how much your AC signal is going to swing. But what you want to do is that you want to make sure that the swing on the negative side doesn't go below the 0.7 volt, okay? Otherwise the transistor is going to shut off during those parts. This R3 is also used. Sometimes you may see circuits where your emitter is connected directly to the ground, but the reason for that resistor is again for the stability, so that the output doesn't depend on your transistor and its specific beta. This resistor and this setup with the voltage divider bias, it's kind of like a negative feedback. It reduces the gain, but it makes the whole thing much more stable and much more predictable. Okay, so I think I'm going to stop here. And thank you for watching and listening, and I'll see you around. Bye.